All right, cool. So I guess today we're gonna cover some functional programming principles using Elixir as the means of which we are learning. So while I go through these slides, occasionally I'm gonna touch base on an object-oriented language. It's a C-style language, so I'm using C# to hopefully appeal to more people, because I could have used like Ruby or Python or something, but then who knows all of those? I don't know. C-style is fairly prevalent, so yeah. Um, First thing we're going to talk about is our first class functions. So I think the ideals of functions are pretty based to everything that you do. So first class basically means that functions can be basically passed around and treated as values. You store them as variables, you can pass them around and whatnot, and then they don't lose their meaning. They can still act on some other value or not on any values, whatever they do. So here we have a functions module, and then we have an addX function. What we're doing is we're returning an anonymous function that's acting as a closure. So we're taking the x parameter argument from our method, or function I should say, not method, and then we're closing around that x in our anonymous function. So basically we're doing a partial application. So we can take multiple arguments, and if we really want to do some fanciness, we do something like this and provide like a helper method. So in this case, we're going to allow ourselves to create a simple helper function that adds 3 to everything that you pass it. I can pass 3 to add x. It will create that anonymous function, and then it closes around that value. So when it does that, it takes all of the names that are used from the parent scope and adds those into the anonymous function scope, and allows you to not really worry about the bindings per se, not worry about like external state modifying that. Allows you to do cool things. So in the second line, we're actually just using that. And some other functional programming languages, you have the ability to treat these passable functions, these first-class functions, a little nicer. In Elixir with anonymous functions, you have to worry about that dot in your call. Get those dots out of here. But it will allow you to basically pinpoint help. That's an anonymous function. It's passed around. You'll get used to it. So we just use it as normal. In C#, you have delegates and lambdas and stuff that allow you to do this sort of thing. So this is our implementation, our C# implementation of the exact same addX function, just in C# land. So we can do similar things in other languages. Java 7 or 8 just added lambda support, whatever it was. So like more and more languages get this functional programming type features that allow you to do nifty functional programming things. So along with first-class functions are higher-order functions. They're very closely related, as you can tell, is that they can higher-order functions can accept other functions as arguments. They go basically hand in hand, but they are slightly different. So in our doX function, we are accepting a function f and a value x, and we're applying that function on the value. So you'll see this a lot in JavaScript world as callback functions. You have something that you're doing, but because it's asynchronous, you have to pass it a callback that will eventually get called somewhere along the line. You have the same thing here. Like your enumerables, when you map over them or reduce over them, you'll pass it a callback function. It's the exact same thing. Those functions that you're passing are higher order. Basically, well, the ones that you're passing them into are higher order functions, so that the map or reduce or whatever you're doing can basically use that when it needs to. Allows you to basically prepare for composition, making small steps in your computations, and allows you to basically separate your concerns into very defined roles. And as we'll see later on, it makes for a lot more testable code, more readable code, because you have single functions that do exactly what you need them to do, and not doing all kinds of extra crud. So here we're just passing that original add3 or that earlier add3 function that we created. It does the exact same calculation, just in a slightly different manner. So in C#, if we have a list of some things, we can use link to basically add stipulations onto this list and only select certain items. So here we are saying, hey, I want all the things in this list that equal value. So we have a list of strings, we pass it a function, blah. So composition. So we're combining simple functions into complicated ones. So here we have a sprockets module. So this could be like a helper module for a model that you might have in Ecto. So we want to get the valid ones. Valid is completely arbitrary here. As we can tell, we're saying all sprockets are round, just because. And then our other stipulation is that it has 12 teeth. So here we're using some pattern matching to grab that teeth amount, and then creating a Boolean value from that comparison. So the composition here is actually using these functions in line with our filters. So we're using the pipe operator to pass those values from one section to the other. So we go from just the list of sprockets in line 12 and go, okay, we're going to pass that to the filter, and we're going to use is round as our filter function. It's going to get all of the round values or all the round sprockets, and then that result is passed to another filter that says, hey, I only want the 12 teeth ones. And so that one is actually going to do some reduction, some filtering, to get those round 12 teeth sprockets. So we're taking our small individual functions and composing them into a larger, more robust function.
Is that a pipe operator in Elixir, the pipe greater than, or what's the?
Yeah, it's two characters, the pipe character and then the greater than. It takes its form from like OCaml based languages like F# and OCaml. They have the exact same operator. It behaves just like the Unix pipe operator that you have on your laptops if you're running Linux or Mac OS. It allows you just to make a nice progression of data, and that's the way you want to treat it. You want to treat it as a progression of data where each step is a transformation. That allows you to keep these steps separate, but then have someone come behind you, be able to read your code and say, okay, I know exactly what's going on. He's going from this step to this step to this step. You don't have to worry about reading inside out or having some crazy amount of parentheses or whatever kind of code syntax that comes with your language of choice. It just makes it nice and simple. So in C# again, we have a similar kind of fashion. Link provides this kind of composition flow by using a bunch of delegates or lambda functions. We can do multiple filters, just like we did before. We're selecting the round sprockets and sprockets with 12 teeth. So we can do similar things again in these languages that we're familiar with. So the next big key point is pure functions with respect to impure functions. So basically there's 3 points that make a function pure. You have to be referentially transparent. It's a big phrase. And all that means is you have a set of inputs, you give it to a function, it always produces the same output for that input. A referentially transparent program will allow you to change any expression with its value, and then the meaning is always the same. You don't have any side effects, as you see in the third point. You don't modify any external state. That basically means that what your function does is all it does. We'll get to some examples here, but really it allows your function to be predictable, and allows you to test your functions just for what they do. You can basically reduce the amount of successful tests and worry about the bad cases. So like if you're worried about, if you're functioning on, like say, an integer or a struct, what happens if you pass it an empty string or a nil value? You can test those, worry about those, taking account for those in your happy values, or you actually pass it integers. You can use some property testing, and just let that be automatic. So you don't have to worry about it because you know it will act the same. Your value might be whatever the value ends up being, but the value will always be the same. Hold on. I forgot a slide. Because I'm going to reference things in the standard library that are pure or impure. So, that didn't come out, right? Missing line. So, some examples of pure functions. enum.map and string.split. So, map will take a list of items and then do some function against those values in that list. That's all it's going to do. It doesn't output to console window. It doesn't ask for some value from the database. All it does is act on that list. That's it. String split, that's a similar thing. It's going to take a string value and then split that into multiple parts based on some delimiter. You don't have to worry about it, asking for other information. What's up?
Is there anything in Elixir to check that something's pure or not pure?
No, sadly. So since it's a dynamically typed language, you don't have the type system to check you on these things like you would in Haskell or Rust or something. So there's no compile time guarantee that you're going to have no outside side effects or any kind of state mutations or whatnot that happen, which is sad, but it's the thing of the beast. You just have to worry about it yourself. Occasionally, I don't know a good way around it yet. I haven't found that. So if you do, find me and tell me, because that'd be great. So an example of an impure function is inspect from the IO module. So if you're not familiar with the function, what happens when you use inspect is that it will take whatever value you pass it and pretty print it into the console, but then still return that value. So in a pipeline function that you're doing, you can throw that in as an intermediate step, and you can basically log that value into your console, but allow that value to still pass through. So the side effect there is that it's printing to the console, which is a side effect, which would mean it's impure. It's great for debugging, but you don't want that happening because one, inspect is slow, it's balls, it's very slow. Two, you may not want to inspect some sensitive data. You may not want that getting out there, so yeah.
Is there a debugger in a command or something?
In log, you can use observer. There's a bunch of tracing libraries that I don't know how to use. because I've never used them before. There's a lot of stuff you can do, like Elixir Release Manager, which uses relics in the background. It's used for like production releases for your code and allows you to do like no downtime upgrades and stuff like that. It has a remote console option that will allow you to attach yourself to a node that's running and then not interrupt its execution, so you can go in and ask the VM for values and observe any kind of behavior that may be going on. I used that a startup that we'd had that basically we'd run the application from an XRM build, and then we just come back in an SSH section and then attach to it, and if anything happened. So in functional programming languages, we don't have your standard while loops or for loops, your standard iteration kind of features that you would get in imperative language or object-oriented language. So we rely on recursion. So in C# land, we can't do this in Elixir. Yes?
Oh, no, I'm
Oh,
sorry.
okay.
I hurt my hand the other day.
Gotcha.
So I'm gonna be-
I just wanted to double check. I don't want to leave you behind. So here we're looping over the values in my list, and here we're doing two things that we don't do in functional programming. One, we don't have a standard loop. Two, we're actually maintaining state in that I variable. So what happens if we're doing something and we depend on that value in our calculation or our accessing of my list, and it gets modified without our knowing or inadvertently? Or say if we forget that, line 14 where we're incrementing I. What if we forget that? We're in an infinite loop and then it just sits there and crashes our app. So that's another nice point. We don't have to worry about that. So instead of looping, we typically recurse over some list. Here we have not a fully defined, I think that's what they call it. Basically, if you have a partial function, it will not define all of the paths. So in Haskell, the implementation of the head function for getting the first item in the list, it's a partial function. So if you pass it an empty list, it will fail. It will throw an error. In our implementation of length, we're accounting for the empty list. So once we get to the end, we will see that empty list and return it 0. So we add it back in. So we're using pattern matching to get the head and tail of the list in the second definition, and then or the second body, and then calling the length function again, and that's how we recurse through. Some of you who may know about tail call optimization, don't worry, you can do tail call optimization in Elixir. We'll skip over that. That's boring. So you can do tail call optimization in Elixir too. So here we're trying to get the factorial of an integer. We pass it in, and then it does factorial combination, blah, blah, blah. So here we're doing a tail call optimized version of it. In this case, all we're doing is that we're moving the calculation, that multiplication, into the argument that we're passing, the recursive call. So we take n-1 and then n times the accumulator. It basically allows us to maintain the current calculated value in the accumulator in ACC, and then pass that as a multiplied value to our current number, and lets it go through.
What is the //?
That is an optional argument. So Erlang doesn't allow for optional arguments of functions. You basically have to define multiple function signatures and then call the next one down with the optional value, or the default value, I should say. So all we're doing here is that first def tfag, we're saying, hey, this is the signature for this function. Here's an optional value, and here are the names that I want shown in my documentation for these arguments. You can set those to whatever you want, and that doesn't affect the next two. So all we're really doing here
Can you
is
show the both versions at the same time?
I
I didn't see
I can-
I didn't see the first version very fast.
can switch back and forth. I can't. I can mirror them, but it's just a pain. So yeah, so what we're doing here is we're just reducing the amount of allocations that we're doing, which reduces the amount of garbage collection that we need to do in the VM, which blah. I did some, when I was doing research on this, I saw that in some cases the VM is already optimized enough so it doesn't matter as much. It really depends on the case. I forgot those cases, but a lot of the times it really does have to do with the amount of allocations that you're doing and the amount of data that you're working with.
It's like, you mean like the number? Because I was reading something there like, you know, if you didn't do tail optimized recursion and you were doing like infinite recursing, like reading a socket or something, then you could, potentially run out of memory or something like that.
Yeah.
Maybe that was it.
Yeah, that could be a problem. Don't want to run out of memory.
So with the tail call thing, the function call has to be an outside part
Yeah,
of the
basically
line.
it has to be the entire call, and you can do other calculations inside of that call. So really, we only need, in the tail optimized one, we only need 2 allocations, one for each argument, when we do the next recursive call. Instead of having, some value in the stack, and then the next call, which also has value in the stack, and the next call.
You don't have to keep the stack at all with the recursive.
Yeah,
you just do not need to remember the stack.
Yeah.
Current value.
I've never been an academic programmer, so that's probably a better explanation of it than what I can give.
Sorry for that.
No, that's, by all means.
Harvard here.
Yeah, I'm not an expert at anything.
So
'Cause
the footprint is lighter.
yeah,
basically.
essentially.
Basically, yes. I mean, you don't have to put it on the stack and keep it. If the stack is significantly smaller than the memory, the heap, so you will finish pretty close with the stack exception. Pretty close. I mean, pretty fast. So,
Yep. And the big thing with working with
because the
VM,
stack is small, so just put the stack.
yep. And by doing that, you allow the VM to not garbage collect as much, which will
Yeah, because
give you less time that it will have some kind of possible interrupt in calculation. So after recursion, we get eager versus lazy functions or evaluation. This is where it starts to get fun. So I have a bunch of text in here. Just make sure I say this right. Eager evaluation always fully evaluates function arguments before invoking the function. Lazy evaluation does not evaluate function arguments unless their values are required to evaluate the function call itself. All right, so we have a range from 1 to a trillion here. What we want to do is we want to map over this list, add 2 to every single element, take the first 3, and then convert that into a list if it's not, which it is.
So you're not running that then?
So actually, the funny thing is, if we create, if we pull up an IEX session, we can't even get past the first step, well, the second step technically. So
You can't
By
just
the-
have to wait a while, right? Right away you run, are you saying you run out of memory? Or?
I won't run out of memory, it's just very slow. So I'm running this on a remote machine. And so when I want to go from one step to the other, so I'm going to pipe this data into here. I'm just going to say to list. So I'm going to convert this range to a list. So it's going to sit there, and it's going to try and create a list first from that range, and then pass it to the enum.toList. By default, Elixir and Erlang are eager evaluators. They're going to take each step in a pipeline. Oh, there we go. Cool. We ran out of memory there. So it's going to take each step in the pipeline and create an intermediate value. And each time you do that, well, you have to worry about a trillion values. But if you look at your code, you really only care about the first 3. So that's where, so that's where streams come into play. Now, streams are Elixir's lazy evaluation maneuvers. So they allow you to take a range of 1 trillion values, pass it around, do a bunch of stuff to it, and then actually get a responsive result. So we can, do the same thing we were doing before with an eager evaluated value, and do this actual calculation within a reasonable amount of time. And I'm not talking about minutes, I'm talking about maybe a fraction of a second. So blah. So I'm just lazy and I don't want to type all of that, so I use a function capture syntax. Stream.take read. So with streams, they are a special struct syntax, and the struct itself contains, if we just leave off that, the struct itself contains the enumerable that we want to act on, and then a list of functions that we want to act. And so this is the actual value that you pass around in between your piped steps. Basically, when you add a stream.map or a stream.filter, it's adding in a function into this list and allows you to not act on that list yet, or on your enumerable yet.
But it's still creating that list.
No, it doesn't actually create the list. So, so the enumerable that we have is a range. Ranges are streamable, so they know how to create these stream structs. Actually, in this case, it's a record, I think. And then there are other facilities that allow you to create streams. And all it is doing this. It creates this special struct or a record, whatever it ends up being. It looks like a record. But it allows you to define the steps that you want to take on the data before the data is actually evaluated. So in the case of our pipeline here, we want to do the same thing we were trying to do before, but in this case, the stream will know, hey, this guy is actually only going to try and take the first 3 values, so that's the only ones that I'm actually going to calculate from that range. So when we run this, we get an immediately returned result of 3, 4, and 5. So we've taken our first 3 values, 1, 2, and 3, added 2 to each one, and then returned that list.
So it looks at a range, and if the following function is a stream, it won't compile a list.
Yeah, it won't. Well, if you take just the range itself, the range is actually just a value. So you can do that just fine, but it's still a range. It's not one value. It's a range. It's an enumerable value. It's the act of doing, piping it to enum.toList, which is taking that range and converting it to a list. So it's that action that caused my VM to crash.
So enum.map will turn it to a list and
Yep.
whatever.
Yeah. So
Whereas this won't.
yeah, enum.map will convert it to a list because it's an eager function.
Each because your first one
Yeah.
had 3.
Yeah.
So
Each
one.
each step you're going to create an intermediate value, and so at each step you create a new list. It just happens that the second to last one, where you take 3, you create a smaller list that you pass into the last function. Whereas in the first step, you create a trillion item list that you passed to the next one. Whereas in stream, you're not technically creating those intermediate values. And then the compiler or the runtime is smart enough to say, hey, I'm going to take this stuff and calculate only these specific values that match these criteria, which happens to be this list of functions that you carry around in your stream.
So those functions in there, like, they've got to be able to tell this. They've got to return something special to tell stream to say stop.
Yeah, so there's these I believe create a special tuple that it returns and basically says if it should halt, if it's okay, or if it's a continuation. So if it expects, so a stream should only, like stream.map will create a continuation. So it basically says, hey, this is going to continue on. It's still going to be a stream value. Whereas enum.list will take that stream and then it will create the special value. I believe it's okay or good to go or whatever it is. And then say, all right, well, I'm going to take that value out of that stream now and then convert it into a real thing. Again, this is one of the points where I know how this stuff works, but I may not be vocalizing it the best way. So the documentation is really great in this area because it'll show exactly what actually happens with the stream.
Like you can build your own stream operations.
Oh yeah,
your own,
you can do this on any data.
stream types.
Like if you had a custom thing, a custom operation that you wanted to do, you could create your own stream for it. Say if you wanted to stream data out of Redis or something. This probably already exists, but you can create a stream to do that. And basically it would just sit there and you can just act on that data as it came in from your Redis server. And then if you by chance got some added value, you could halt that stream.
Can you name a stream and continually access it?
Name a stream.
Like say I wanted to run a function on the stream to get the next 3 numbers.
Okay. That I'm not sure of. That's more of like a generator syntax, which I'm going to show you. It's a way to get around this in C#. There's probably a way to do that. I'm not sure though. So like exit. So in C#, there is no lazy evaluation, so you kind of have to fake it until you make it. Here we have a getPrimes method. It returns an IEnumerable of integers. So what we're doing here is we're looping forever in our while true. And then if our calculation of is prime on the current counter is prime, we're going to yield that value. And what that does is that it basically creates an iterator, so we can, or iterator, generator, whatever it's called. It allows us to continually poll that function for the next value. And then we get an infinite thing that we can act on, but then we could also not act on it. So we don't have true lazy evaluation, but we can fake something that kind of looks like it. Last big thing are types. So we briefly touched on this earlier, but Elixir is a dynamic language. It doesn't have a strong type system. Like if you want static analysis, you'll have to use dialyzer to do this, not at compile time. There are some checks that you can have at compile time, which include what we have here. Pattern matching is going to be the biggest thing you use for type system. You'll be able to split out values, match on specific structs or maps, or if you want to pattern match only on a specific set of tuples, you could do that. Structs being the second biggest thing you're probably going to do on the type, custom type stuff, because when you create models for Ecto, or if you create some random container that you want to hold data, you're going to create a struct most likely, because you can match on that a little better than you can with maps, because you can match specifically on the type and not all possible values of that map. So structs act as maps. You can use them in the same positions. They have a couple extra things that you can do with them. So the next few things really allow for extensibility in your code. Behaviors act as a type of interface. You define a set of callbacks that you want implementers of your behavior to have. A good example is plug. So plug has a behavior specification that it has for any plug that wants to be a plug. It has 2 functions in it. init and call. Init takes one value, which is a list of options. It's a keyword list. And then call will take a connection and that list of options. So you know each time when you see a plug, if it's really a plug and not just a module that acts as a plug, it will always have those two functions. You'll basically get a warning at compile time if an implementer of a behavior doesn't implement all of the methods or all of the functions. It's not a thing where it'll fail. There might be a flag where you can set it to fail at compile time, but it's not going to fail at runtime unless it comes across a situation where, hey, I'm trying to call this function and it doesn't exist on this implemented module. Yeah. Protocols are similar, but they're more aimed at the kind of polymorphism side of things. So with behaviors, you call the function of the behavior on the implemented module. So in plugging in, we don't go plug.call and then pass it a value that we're supposed to act on. We actually call the plugs call method. So if we take into plug.router, so the built-in router in the plug library, we'll say plug.router.call and then pass it the connection and then the list of options. We don't have the main plug behavior module do that call. With protocols, we do. So we have a protocol specification where we define a set of callbacks just like we do in a behavior, but we have implementations that are connected to that default module. So when we call, so there's an enumerable protocol. So all lists are enumerables, ranges are enumerables. When we call enumerable dot reduce, we're calling it on the protocols module and not the implementations module, which is tricky. I'm going to try and show that in an example of code. I don't have anything that's good enough, so I'm going to actually reference the Elixir Lang standard library. So we are going to come over here and pull this up. Well, actually, let's take it to the stop here at plug, and I'm going to show you what I was talking about with its behavior that it has. So if we come in here and come into the lib folder and then view this first file, this is actually where the specification is. It has a bunch of documentation, but the key points you want to see here are, yeah, sorry.
What does plug do?
Plug is a middleware stack for applications. It has a set of defined adapter specifications and middleware specs. So the plug spec is the middleware, and then you have HTTP adapters. So right now the only official one is Cowboy, but it behaves like Rack in Ruby or Ring in Clojure, where you have this specification and a lot of libraries can consume that specification and allow you to do some pretty nifty stuff. So Phoenix, which everybody's probably familiar with, is the biggest framework in Elixir. It's entirely built on plug. So all of the benefits that it has on the plug pipeline, the call stacks and the middleware that you can do, it's all thanks to plug. That's what it's designed for. So if we come in here, we have a use statement of behavior. So what we're saying is, hey, I'm defining a behavior. Give me the def callback macro. That's all, essentially what it does. And we define our two callbacks, init and call. So as I said before, we know that all init functions on plug implementations will accept a list of options and will return a list of options. The call function will accept a connection and a list of options and return, presumably, a modified connection. This will always be the case. And if we step over into an actual implementation, so let's get one that's easy, like head. So what this does is it converts any head requests that you get as a web application into GET requests. It allows the underlying web server to not have to deal with the head request and just response, so it doesn't fail. So what we're doing, our implementation of init, we don't really do anything special with our options. We're not going to modify it in any way. So we're just going to return whatever. And then our call implementation, we really only care about requests that come in that have the head as the HTTP method. All the other ones we're going to ignore and just pass through as normal. But our head requests, we're going to take that connection and we're going to modify it, which is what we're doing here. We're taking our original connection and then we're updating it with the map update syntax. That's what this is. So this pipe just says, hey, everything after this are new things that I want to update. Any existing value is going to be my given value. So here, all we're doing is we're changing head to get. All right, so.
Which is also the way I go works, like your update, because it's basically a map.
Yeah, it does a lot of stuff. A lot of that is map updates. So that's basics of behaviors. So to get into protocols a little bit, let's take a look at Elixir's documentation, or it's sourced. Here, Elixir. There we go. So, where is that? I forget where this is. Collectible. So we'll just look at collectible. I don't know where the enumerable one is. But basically, if you want to do any kind of traversing of lists or maps or whatnot, and move those values into another enumerable, collectible will allow you to do that. So when we define our callbacks, we're saying, hey, this protocol only has one function that you really need to worry about, and that's into. We want to take, this collectible, and we're going to return essentially a function. That's really what we want. We want a function that takes some command and then appends some item t to that term. So in the list, talking about lists, we're going to take an existing list and we're going to append some value to the front of it, put it on the head of it. So for lists, actually, we are defining our implementation for list. And then our function body defines everything that's necessary for this implementation of collectible. Now, it does a lot of fanciness that, honestly, I'm not even really sure exactly what's all going on. But the big key points you want to hear are this const, atom, done, and halt. So these are those states that you pass, that you could pass in like a stream. They're doing it here in collectible as a way to know if the collection process, the traversing process, is successful or not. And then when we actually want to call this on a list, here we're actually using enum.into as the public API for this, but all it does is call that function on the collectible module. Go back. So we come down here, enum again. My favorite, because Oh, there's that protocol, enumerable. So let's go into. Oh, all right. So what we're doing eventually, there we go. Bread and butter of into and the enum module. You get eventually down to this do into function. And here is where we're calling that protocol, that collectible protocol. We're not calling it on collectible.list.into or whatever we might have named, or in this case, list is the module name for dealing with the list data structure. We're not calling list.into, we're calling collectible.into. This is where the polymorphism comes into play. We have one single public API for calling these functions, and the compiler will actually do the magic bits in the background. It creates a special naming convention for protocols and will compile your implementations into this special form, which is why there is a compile protocol step in the compilation process for production environments. So when you do this in dev, it treats these implementations as separate modules, and then when you do this compile in production, it will take your protocol implementations, combine them into something I don't know because I've never looked into it, but it allows your code to run faster, so that's always good. So you compile your protocols, and you will have a consolidated directory of basically all of the implementations for that specific protocol. It allows the VM basically to load the bytecode faster. So that's the cool part about protocols. A little bit trickier to work with because if we look at this again, all callback functions for protocols have to have the first argument has to be the type that you're going to be acting on. So in collectible.into, our implementation for list, it's very dependent on the type list. Like if you don't pass the list, it's not going to hit this implementation. If it's a bit string, it's going to go into the one below it. If you want it to act on a list, you have to pass it a list. And that's a nice little type checking that comes with it. Whereas with behaviors, your functions that you define, they don't have to take any arguments. You could have just something that says, say, if you're writing a parser behavior, that eventually you'll use to parse YAML and JSON and XML. You can have an extensions callback function on your behavior and say, all right, I want all implementers to tell me what extensions they support with this specific parser. So if you have parsers.json, it's going to have extensions that says JSON is one of my supported extensions. Well, we don't have anything that we're acting on in the case of the protocol. It's just we're just returning a value. You can't do that with protocols. So a lot of the trickiness that I've tried to do sometimes with protocols hasn't worked out because of that fact. That's one thing you have to keep in mind when you're doing this. Where, should I use a behavior? Should I use a protocol? It depends on the situation. I find myself using behaviors more just because they're a little bit more flexible. But you do have to pass around like the name of the module that you need to use. So that's one downfall.
What happens when a protocol receives something it doesn't expect?
So when it receives something it doesn't expect, the default behavior for it is to throw, I believe it's a not implemented error. And basically says, hey, for this specific data type, I don't have an implementation for this protocol. I don't know what to do, so I'm going to throw an error and then let the VM just come back up.
You catch that error?
You can. So you can create an implementation for the any type. You can pass instead of list here, you can pass any and return basically a dummy value. So if there's a good explanation of this, or walk through this on the Elixir Learning site. So they define a protocol blank, and all it does is say whether a given value should be considered blank. It returns a Boolean value, or true or false. So what we're doing here is that we have integers. They're never blank. A list, only empty lists are blank. All the other ones are not blank. For maps, we're saying if the map size is 0, then it's blank. If it's not blank. And then for atom, these specific values are blank, or true, false and nil are blank. Everything else is not blank. But you can take, here it is, undefined error. This is what happens when you don't have an implementation for a given type. So there is a way to catch all of those, and that's by using any. So any is a special name. It basically provides you a default fallback. So if you want a catch-all in your blank implementations, you say, okay, I know anything else that I'm going to pass it, I want to consider not blank or blank, whatever you want to choose. And you don't care about the input value, most likely. Just give it a specific return value, and that's your catch-all. I don't do a lot of protocol stuff, so this could be potentially useful, especially in like parsers and stuff. But typically, you'll want to have a set list of implementations that you expect, and more often than not, you're going to fail on the ones that you don't expect, because then that means your library or your application is getting used in an unknown way, and you want that to fail.
Is there any difference in performance between behaviors and protocols?
Yeah, so
It seems like it could be, yes.
So that's where I touched base on the compilation process. With behaviors, they act as normal modules. There's nothing fancy about them. They just have some compile time check that says, hey, are these methods implemented on this, or are these functions implemented on this module? For protocols, there is a lot more going on. So in your dev and test environments, it's going to be a little bit slower, but there's a production thing that you can call.
Okay, what you said, it compiles.
There's a mixed task. It's compile.protocols, and what that does is it compiles every single implementation that you have of a particular thing. Yeah, and so you'll end up seeing. Oh god, what have I done? So you'll end up seeing pieces where you'll have build consolidated. Okay, that's the actual path that you would do. So where build is your standard build directory, prod is your environment, and consolidated is the directory that it creates for your protocol implementations. And it will basically combine all the implementations for each protocol into a single Beam file, so that you pass this directory to Elixir, the runtime, and it will use that directory and then not have to look everywhere for all of your implementations. And I think that's how it does the improvement at runtime. All I know is that you don't do this. I think it's built in now. If you didn't do this before, your stuff is slow. You add this, and it's fast. And so lists, this is just some fun code time stuff. We'll dip into IEX and then look at the source code. And this is really the last thing. So lists are your basic data structure you're going to use everywhere. Keywords, so like you can access a keyword list with a particular atom, and it will give you a value if it's there, or nil if it's not. Or hash sticks, where you have a string key, and then using some hashing algorithm it stores it in some thing. And maps, like you have a key value stored. But you can enumerate all over those, and keywords and hash sticks are actually just lists. They have a special formatting because they're useful and you get used a lot, but they are, each one is a list of 2 atom tuples, a key value. Where in a keyword list, the key is an atom, hash stick, key is a string. You can enumerate over those lists and pattern match on the tuple itself. You don't have to worry about having 2 specific values that you get passed to your function. It's a single value you get the tuple because it's the value for that part of the list.
So this is index and tuple is not, is that right?
It's basically, you can't like enumerate over a tuple. You have to know the length of the tuple to get the values. You can get specific values from, say if you needed the 3rd value in a tuple, you can get that. Just say, you pass it to the lm function. So
It's more runtime.
yeah, it's more runtime work because with dealing with a lot of lists, you usually don't worry about the order in which you get the values. It's more about, hey, let's just work through the values, transform those values into doing something. So if we have a tuple here, let's say this one is you're going to see a lot, and some magic value. Okay. All right, so our tuple is a 2-atom tuple. You'll get this a lot. Either your atom's going to be error, it's going to be okay. Basically, just some runtime checking of success and failure. So here, what if we don't care about the tuple, the atom itself? We really just want the value. We know it's always going to be a string. We're just going to pass it to something else. Well, we can take tup and pass it to lm element. So we're getting the index of 1, so 0 indexed. So we can get our string. You would use something like this. I do this a lot in testing, where I want to assert specific values for each of these. Where in a production environment, I would pattern match on those values. Yeah. So in a list, we would have something like this if we wanted to use the exact same values. So instead of lm to get the specific elements, doing that kind of sort of thing with something that's not at the head of your list could be time intensive. You don't know the exact position of something, and plus you have to deal with creating new lists in an intermediate stage. So you'll often deal with head and tail of a list so that you can get specific values based on what's up front. Give me the next value. We want to take that one and then do something with it. So here, our head and tail, we get, okay, a new list of YOLO, right? We saw that before. What if, what was I going to do? I don't know what I was going to say next, but basically we want to just process this list. So that's where we would come into play with map. So map, it expects your enumerable as the first argument and a function as the second one. So in this case, we want to take our list and then we're going to pass it to a function, and this function is going to inspect a value. So we are lazy. we don't really want to do anything, but you want it to pass through. So what we're doing, we're looping through. I can see how I said that, looping through. We're looping through our list, right? We're going to each value. We're getting that value, and we're passing it to our function. In this case, all we're doing is inspecting it. So we get the printed out values, OK as an atom representation, and YOLO as a string representation. And then we get that list back. So the yellow list that we get back here is actually a result of map. Map will just allow you to pass through these values, do something with them, and then let them continue on as the modified selves. So if you modify a value in your function that you pass to map, that modified value will be represented here. So if I wanted to actually do something where we modify the value, I'm going to take our value x and then add cool at the end. So we have OK cool and YOLO cool. So what we're doing, we're what is that? I always forget the damn word. We're concatenating strings. I forget the actual thing of using interpolation, string interpolation. Thank you. So all we're doing is injecting the string value of each value into a new string, and then our new list that we create with map is just a list of strings, whereas before it had a list of heterogeneous types. It had an atom and a string. Now we just have strings. So the next thing that we could pass our resulting list to could work with those strings and deal with them. You see a lot with like filtering and mapping like tuples into usable values. So you could map over a list of tuples that have responses, just like this, where we have OK or an error-based tuple, and then if it's OK, we grab a specific value, and if it's not, we may return nil, and then in a later step, we filter out those nils to do whatever you'd like. The other big list function, I could say, is reduce. So if we look at enum.reduce, so reduce is something you hear a lot. You take a list of values and you reduce it into one value. You could take a list of strings and make one string. A list of metrics that are floats, combine it into a single value. Or a list of lists and combine those internal lists into single values, which provides you a list of single values. It's called different things in different languages. Some functional programming languages call this fold. And then they have different ways of folding. You can fold from the left and fold from the right. It basically all does the same thing. You have a collection. So in our examples here, we have 1, 2, 3, 4. And again, we are going to pass it a function. But if you notice, this function takes 2 arguments. This takes x and an accumulator. So by default, accumulator is nil. And then you use this accumulator to act as the current value of your end result. So in this case, we have a list of integers, and presumably we want a single integer at the end. So we're going to take this function, x, an accumulator, and what this does is it multiplies x against that accumulator. So the first value is the accumulator basically takes that first value and makes it itself. So in this case, the accumulator will end up being 1, and then you'll multiply 1 by 2, and then 2 by 3, and then 6 by 4, and that's how you get 24. So we're we're iterating through this, recursing over this list, and then our function basically keeps track of our state and the accumulator, and allows us to combine these values into a single value. What if we don't want the reduce function to make a guess at our first value? Treat it as nil.
That's what it's doing.
It's basically it's a defaults to nil, but then essentially what happens is
No.
what?
It defaults to the first thing in the list.
Yeah, but it really
Which isn't nil. It's whatever the first thing in the list is.
it treats it it's really nil from what I remember.
It
It's
says
nil.
right up there. It uses the
Oh
first value.
well, that's what it ends up being anyway. Is it? I think it's something whatever. Cool. You read more than I do. I don't really. I don't read. But what if we want to control that starting value, right? Well, there's another signature. That's 3 elements. So it takes that list, that enumerable, a starting value for your accumulator, and then the function. So in this case, we want to start with 0, and so we add these values, and we get 6. If you want to reduce a list of lists, but you want to make those values into, say, a special thing, like a hash stick or something, you can start with a hash stick. It doesn't really looks like a list, an empty list, but you can treat it as hash stick. So you can do hashstick.new, and then creates a new hash stick representation, and then you can work with that. It's all allows you to choose your route and work with the values as you see fit. You see a lot of reduce and map working together, hence the term map reduce in like cloud computing. You'll have distributed nodes that map over a bunch of values, and then you have a bunch more maps, a bunch more nodes that reduce those values that were just mapped and get these single values. You see a lot in analytics and whatnot.
What's a hash stick?
It's a special. So what language do you use a lot?
Ruby, JavaScript.
So in Ruby you have a hash. It's kind of like that. So the storage, the in-memory storage, has some hashing algorithm that allows you to access random elements a lot faster than you could normally if you had to iterate overall.
In Elixir, there's a map and a hash stick,
Yeah.
which are similar.
So hash sticks only accept strings as keys. Maps can have strings or atoms as keys. And when maps first came around in Erlang, they were slow. So you'd want to use a hash stick. They may not even be around anymore. They probably are, but like you would use hash stick to get better performance out of a map type situation, because maps were slow for high count, high volume data. So if you had a lot of keys, it would be slower if you use a map. So you use a hash stick to keep your performance up. So like use a lot of reduce, you use a lot of map filters. If you're working on infinite or very large data sets and you're only concerned with a small set, use their stream counterparts, because then you can get those benefits that we discussed earlier. But yeah, those are the key points. Oh, here's the nifty part. I'll leave this as the ending piece. So we come back to enum. Reduce is such a useful function that here's the implementation of enum.map. You see there's an enumerable protocol that we use, and we call the single reduce function that follows the exact same signature, essentially, with some extra bits for the protocol itself. But we're using a single reduce function to implement map. And all we're doing is that we're starting with an accumulator of an empty list. And so at each succession, we append a value to that accumulator and allows it to go through. So our map is really a reduce. Our filter can be implemented as a reduce. So if you want to work on one thing with lists, get comfortable with reduce because you can do a lot of stuff with it. So yeah, that's that. So any other questions, critiques that, hey, you should stop talking because you suck?
That's great, thanks.
Awesome.
Did you learn Erlang first? Or
I touched base with Erlang briefly before I did Elixir. So I found Erlang and said, hey, this is nifty. It's a lot better than what I've been using before. So I looked at a framework called Chicago Boss. It's a full stack framework that does pretty much everything for you. I was okay with it. I was comfortable. But then I came across Elixir, and the documentation was better. It was more inviting, so I had a lot more there. Created a few libraries, learned a little bit, really dug in Elixir, which allowed me, conversely, to dig into Erlang because it's so dependent on Erlang. You have to know about supervision trees and how processes handle themselves in a runtime environment. So you need to know about Erlang to know about Elixir. But it's easier to kind of gently go into Erlang through Elixir because you don't have to worry about it so much. If you come from a comfortability with Ruby and its syntax, or even Python or something close to it, like you can read Elixir code and be like, okay, I can kind of figure out what's going on. I can see what's happening. With Erlang, not a lot of people do prolog programming. You don't know what's happening. Why is there some random semicolon in between a repeated function that has a different body? Why do you have to end the last one in a period? These are real things in Erlang that you have to do. So it's tricky, and you have to learn all these weird things and then read a bunch of crappy documentation that, it's very dependent on you having a lot of knowledge. So if you're new to functional programming in Erlang itself, it's not as inviting as Elixir. Yeah.
Is there anything that's very difficult with this functional approach? Usual construction is that in object-oriented that you have some object and you keep some state inside and it's a private state, yes?
Mm-hmm.
And you do some some functions, some methods, and keeping or changing the state, yes? So is there anything with this functional approach you're struggling with if you go to make it? If you want to make it, really functional, purely functional.
I haven't yet.
Okay.
So a good object-oriented example project is a bank account. So usually you have an object that stores your account balance,
Yeah, exactly.
And then you have methods that act on that balance, whether you're making a deposit or you're doing a withdrawal or what have you. So you have that internal state, right, in your object that's private. You can't touch it except through your public API.
Yeah.
In Elixir, you can achieve a very, very similar thing, either by using a gen server or a specialized form of it called an agent, or many other different ways. Essentially what these do is that you would call somewhere in your supervisor, you say, hey, I want to add this child, and it's the supervisor. It acts as a server. And then that gen server will say, okay, I'm just going to loop on myself. I'm just going to loop here. And while I'm looping, I'm passing myself a value. That value that I'm passing myself is my state. So in a bank account situation, you can keep your balance in that state in a process just for a particular user. And while it's looping, your gen server can receive messages. And that's the big thing about active pattern. You can pass messages from one process to another, one node to another. And so the messages that you'd pass this account balance gen server or an agent are things like check balance that would return a current value of your balance, or add, or make deposit or withdraw. So these messages that you pass it, you can basically send it a tuple with an atom and a value, or however you want to construct your message. You send it that, and then your gen server, as it gets to that message, will respond with its current state, and then allow it to act on that state. You can modify the state with a message. You can just return it. You can do nothing with a message, whatever you do. Let's see. Yeah, so we're briefly touching on this, but there are ways around getting through these kind of state-dependent situations that you would do a lot in object-oriented programming. Since it's a VM, it's never going to be as fast as like C or a similar language. So if you're doing stuff that's really time sensitive, like creating a hash in some certain value, you'll usually see a NIF created for that. It's I forget what that stands for, but essentially you're doing foreign function of an invocation through that NIF. It'll create an Erlang or an Elixir interface for a C function, and you can call it from Erlang. That's a downfall, I guess, in this kind of world. In others, like Haskell, it's not as big of a deal because the calling from Haskell to C isn't that bad. Whereas in Erlang, your NIF process could fail, which then, if you don't have it set up correctly, will kill your entire VM or your entire application. So if you don't set up things in the right way, it will fail. Or if you use the wrong library that uses NIFs, that it could break down and kill some performance intensive or performance dependent part of your application. But as far as I can't do this one thing in functional programming, I haven't found it yet. Mapping kind of data algorithms is a lot nicer in functional programming. You can use things like pattern matching, or in more strict typing, you can use the type system to model it for you, and then use the language to work around your types. And then your types give you assurances, both at runtime and at compile time. So there's a lot you can go into, but I just want to touch briefly on some of those things.
I thought it was a pretty thorough explanation. I was trying to find this diagram because they were talking about like functional object-oriented processes.
Hold on.
And then it's like.
I don't think I have that exact one, but I favorited this image.
Okay.
Just for this purpose. Let's find it. Favorites. It's a recent one. Image. Here we go. So this comes from Joseph Verlaine. It's very similar. So you have O patterns and FP patterns. So if you notice, FP patterns, they're all revolving around functions. Everything's a function. That agent and gen server implementation I was talking about is really just a set of functions, where all of your state is maintained by a recursive function. O patterns, you have all this stuff that you have to know. Like strategy pattern, I do O programming all day at work. I don't know what strategy pattern is. I probably haven't used it. Visitor pattern, I think I've used it once. Yeah, like you have all this stuff that you have to worry about in OO because you have to worry about the state that can be modified elsewhere. Who knows where it could be modified?
That's what the fucking problem is the state, like the concurrency model, right? We know all the languages have your state is just this global shit that any other thread can come through and like ruin your state. And you have race conditions and everything.
That's why you have to have locks and mutexes and semaphores to get around that.
If you have this process model like in Erlang, like the state's just in that process in that function call. It's arguing to that function.
Yep.
No other thread's going to mess that up. And then you don't have to worry about hiding your state, reporting it, hiding it away, keeping it safe, and grooming it, giving it haircuts. And
that's where message passing comes into play, because you have another process that may want to act on that state that another one's keeping. You send, process A sends process B a message saying, "Hey, I want you to update your stuff, update your state, and do this thing to it." Well, it allows you to do that, and then process B will respond to process A and say, "Everything's good to go." That's it.
But still, I mean, when processing a message, so it will not be broken. It's atomic, yes, in processing the message. So, but still, you can send messages, and you can be raised between them.
Yeah. So it's not
different. Other actors send messages.
It is asynchronous.
Yes.
So you'll program your.
But it's still you have to think about it.
Your
model of concurrency.
The thing about message passing and actor pattern is that if you're using a lock in object-oriented programming, if you have a process or a thread that tries to access a locked data, your thread's gonna fail, right? It's not gonna like that lock. It'll wait. So that's for concurrent and distributed applications. Waiting is as bad as failing. So with message passing, this is all asynchronous. Each process has its own mailbox. So other processes can send a bunch of messages, and it really doesn't matter the actual order. It's about the eventual consistency. And so your main gen server will have its mailbox, and it will process those messages as it can. And then you can use some throttling and stuff to kind of choose for that.
It's different, but still you have to think about it.
It's different.
It's different, but still
you still have to think about it, but it's a lot senior when you think about distributedness.
It seems to be a lot simpler.
Yeah, it's a little simpler. It's a lot more straightforward. You don't have to worry about what happens if I have the dining philosophers problem, where you have a set of philosophers and then only a certain amount of forks to use, and they all have to basically have 2 forks? 2 forks at a time, but there are 10 forks and 11 philosophers, whatever it is. But it's a concurrency problem. How can you schedule out those philosophers to eat?
There is no solution without the color. I mean, the waiter.
Yeah.
Without the waiter, there is no solution without. I don't know the English word, sir. But in fact, yes, it's pretty complex.
Yeah, it's a.
It's not murder, is it?
No,
I don't think it's murder.
No, it's like starvation. Okay, so there is no solution without. There is no solution without an additional waiter to make a solution without starvation. So that eventually everyone will get the chance to become 2 forks. So it's pretty complex.
Yeah, but
here
so
we don't have. I mean, it's much cleaner.
There's a lot
It's
going
a
on
model
still.
of thinking about the concurrency.
Mm-hmm.
You
Very
share
true.
nothing, you just pass messages.
That'd be nice. Eventually, you have to think a little bit. Yes.
So, what is about the courage to try working in a purely functional way?
Yeah, it takes a little bit. So let's stop this.